the workshop on transformations and symmetry. I'm Tony Bearden. I founded AIMSEC over 20 years ago now.
Hi there, my name's Elizabeth Turock, and as you can hear from my strange accent, I'm not from South Africa. I'm originally from Scotland in the UK, but I've lived here in Cape Town now since 2008, so that's quite a long time ago. Anyway, we've prepared a nice workshop for you today, and we hope you're going to enjoy it.
So, as most of you know, Elizabeth is one of the AIMSEC team, and her brother-in-law, Neil, not her husband, her brother-in-law, is the person who started AIMS. He had this vision of the African Institute for Mathematical Science, of which AIMSEC is part. But that's only one of the things we can say about Elizabeth. We can say many things, and she's as I say, she's an invaluable member of our AIMSEC team. Okay, now to the program. What are we going to be talking about and thinking about this afternoon? Well, as usual, we are featuring this spiral learning. So we're going to start with what sort of things you teachers could do with the very youngest children and gradually make our way up this spiral, adding more and more ideas, but always about transformations and symmetry. So the topics it will all be investigating and learning more about is transformations, and they include reflection, rotation, translation, and glide reflection, 4 of them. Now, I say 4 of them because today we're going to concentrate on those 4 rather than enlargement. So the property that the 4 of them have in common and do not share with enlargement is they keep all the angles the same and the lengths the same, whereas enlargement, as you know, is where we come into similarity and things get expanded or shrunk when you're all in the same proportion when you're talking about enlargement. So today we won't be dwelling on enlargement. We'll make that the subject of another workshop. And symmetry is a study of the transformations, really. That's what it is. Okay. And we're going to be climbing up this learning spiral round and round. And so we're going to start right at the bottom here for what we might do as teachers with young children, which will involve pictures and talking about the pictures. And then we'll be coming on to reflection, looking at mirrors and see what the effects of reflection are, and then rotation. And then we're going to have some pictures showing rotational symmetry and reflection symmetry and analyzing those pictures and those particular transformations. Looking at mirrors at different angles and reflection in parallel mirrors. And then this glide reflection, which is a little bit different to the simple reflection. We'll look at freeze patterns, and then you'll do a symmetry challenge, which involves working systematically to find a lot of solutions, all of them, and there are more than 60 there. Now, during this workshop, we're going to suggest, and I apologize perhaps if you have heard this one before, but as teachers, it's really valuable to actually do the tasks. And today, please do these tasks as if you were a learner doing them. And you then will begin to appreciate what the learner's doing. You know a lot of these facts, probably some of you know all of them, but how do you apply what you know to the tasks? Well, first of all, do the task yourself, and then reflect as a teacher on what your learners could learn and how you could guide the learning. Elizabeth.
Okay, so let's have a look at this slide. We have to have a look at the butterfly and a pair of hands. So what do we notice? What are the similarities and the differences in the 2 pictures? So as I'm looking at it, I can see that one of the similarities is that the butterfly and the pair of hands has got a line of symmetry straight down the middle. But if you take one hand on its own, it doesn't have a line of symmetry. So if you just hold up your own hand, you can't find a line of symmetry. But if a pair of hands, you can have a line of symmetry right down the middle. And if we look at this picture, we can see this elephant. And if you look, you can see the reflection of the elephant in the water. So where would the mirror line be? So the mirror line would be between the elephant and the water. And then if you look at this picture of this lady who looks very familiar, oh yes, it's Tony. It's Tony pointing to her right ear or to her left ear. Well, first of all, let's look at the picture of Tony where we can't see her face. In this one, is she pointing to her right ear or to her left ear? I think we would all agree she's pointing to her right ear. Now look at the reflection of Tony in the mirror. Which ear is she pointing to? In the mirror, it looks like she's pointing to her left ear. So what's happening there? The mirror is reflecting back the image in front of it. So it doesn't take into account left and right. It just reflects back what it sees.
In fact, it reverses the image, doesn't it? It turns left into right and right into left. And the interesting thing is that I appear the same distance behind the mirror as I'm actually standing in front of it. And that's the feature of, Elizabeth said that the mirror line is between the elephant and the water. It's exactly between, so that every point is reflected to another point that's exactly the same distance on the other side of the mirror line. Straight through, and that's why my right ear appears to be my left ear in the picture.
So what do we notice about these pictures, and where are the mirror lines in each picture? So we've got a lovely picture of Mount Hood, Oregon, and the Mirror Lake, and we can see that there's a hill with snow on it and some grass and some trees in front. And you can see that reflection in the lake. So where would the mirror line be in that picture? Do you think? It's a pity you can't communicate, but I think the mirror line, as you would imagine, it must be in the middle of the picture horizontally.
Just so calm that it looks like glass, just exactly.
Yes, yeah, it's perfect, isn't it? Now, looking at the other picture, which was taken in a place close to where I stay, which is Fishhook in the Western Cape, we can see some sort of dinghies with masts on, and you can see the reflection of those dinghies in the water. And you can also see some people standing there at the side, and you can see their reflection in the water. So can you visualize where the line of reflection is for, well, let's start with the dinghies. Can you see the line of reflection there?
Well, I think this is interesting, isn't it? Because each boat has its own reflection.
Yeah,
and that means that, for example, if you go to this one at the back here, the mirror line is just
in a different place.
Yes. Whereas if you come right to the front here, where you see these people, the mirror line is somewhere. If you can see my cursor moving, it's sort of there. So that picture's got many mirror lines in it.
It has,
which is quite interesting.
Here we can see a canal with barges on the canal. And again, you can see the reflection of the barges in the water. you can also see the reflection of the trees in the water. So the line of reflection, where do you think it would be, Tony?
Well, I think for this blue boat, it's sort of here.
Mm-hmm.
And for the sort of brown boat, it's more up here between, you know, boat and the water there.
Yes.
And canals, I mean, a little bit more to us in the UK than they would in South Africa, because going back in history, these are man-made riverways that were built all over the country, and they were the routes that people used to get from place to place, but also to get goods and you know, to take loads from one place to another. And they were pulled along the canal by big horses that walked on the canal bank. And this place, Ormskirk, is very near where I was born in the north of England. And there were canals that you could take one of these barges on and travel all over the country. And I'm sure there were canals in Glasgow.
Oh yes, yeah, lots of, in fact, they're still, well, they're probably still there where you were born too, but so they're not so well used as they were back in the day, but they're just used for people to walk along and enjoy
Yes,
the peace and the countryside. So it's quite nice.
So what do you think of this picture, and what do you notice? It's interesting, this, and there's a lot to see in it, and quite a lot to explain too. So what do you see in the picture? What do you notice? What do you see? This young lady is obviously taking a photo, okay? In some sense, she's taking a selfie. Have you ever seen a selfie like that? And it's not actually a very revealing selfie, because we can't even see her face. She's got a camera in front of her face. But how many copies of her are there in that picture? And why are those copies? In answer to my why, there's a one-word answer there. Infinite, says Pamela. Yes, infinitely many. I mean, it seems to go on forever. Sort of along, you know, we see this girl with her camera, and then we see her again and 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 so on. And it gets a little bit dark and not very clear at this far end, and Pamela's absolutely right. But that wasn't the word that was in my mind. It's a good word, actually, and I would agree with Pamela 100%. Yes, infinitely many copies, and the one word to describe it. What explains it in a way? Okay, so the one word is reflections. Many. So there must be mirrors involved, and we're going to come on to an explanation of it. And now here's another. What's happening in that picture is what I'd like you to say. What do you see in it? Just what do you see?
But it's a tunnel. What shape is the tunnel? It has a lot of mirrors in the tunnel. What shape is the tunnel that these two people and I was walking behind them? Hexagonal, as Pam says. So it's like a hexagonal prism, but it doesn't have the two ends. It's got open ends. And so this exhibition is something that's going around the world. So there's no reason why it shouldn't end up in South Africa and other countries. Some of you might be lucky enough to have it. And it's all based on mirrors. It's based on light and mirrors and optical images. It's about optics. And this is one of the many mirror exhibits that they have. And it's very experiential. This sort of thing, they've got another opportunity to have the infinite images, and they've got works of, I believe they've got works of Escher in it, if I remember. I'm reaching now. This is pre-COVID. My mind's had a reset since then.
Caroline is going to show you how you can set up the sort of images that you saw on the last slide with the girl taking photos and selfies, I called them, and this picture, how you can set that up in your own classroom. It's a hexagonal tunnel, and two people actually are just walking through the tunnel. And Caroline's going to show you how you can set this up so that your own learners in school can see this. Now we're going to look at a different sort of transformation. We've been looking so far at reflections, and now I want you all to stand up, please. And please do it. So Caroline, perhaps you could, I don't know whether you're in the sort of place where you could do this and show us, but anyway, everyone should stand up, and we're not going to check on you. But if you can, you should stand up and face the front. In other words, well, yes, face your computer. So your computer, yeah, you're just facing the front. Now I want you to turn all the way round.
All the way round.
All right, she's turned all the way around. Now, will you turn to face the back wall? Now, will you point one of your arms out to the side? Right, now will you turn to face the side wall on the side where you're pointing to the wall? Will you turn back to the front? Now, will you turn to face the side wall on the other side of the room? Now, thank you, Caroline. Now, you can make up your own directions like that. So that's a people mass activity. Why do it? Well, you can ask questions like, ask your learners, can you describe how much you turned? Now, or according to whether they are younger or older, they may know about degrees, they may not. So they may say, well, they turned all the way round or halfway round. They may say a quarter way round, or they may say they turned through 360 degrees or a complete turn. Or they may say they turned through 180 degrees. So there are different answers, all equally correct. And so you can help to develop. I mean, you might even do this when you're introducing angle in the words about degrees, and teaching your learners about angular measure, degrees. So can you describe that another way? Well, they might describe it as a quarter turn, or when that was to face the side wall, or they might describe it as turning through a 90 degrees. And another way, which you haven't mentioned yet, is turning to your right or turning to your left. Now, the same thing can be described as turning clockwise or turning anti-clockwise. Okay, now maybe that was reversed in the picture you saw of me, so don't take too much notice of that. So did you turn clockwise, like the hands of a clock, or did you turn anti-clockwise? And that's why there's a picture of a clock on this slide, because it's a very good image, as long as it's a clock with hands that go round and not one of those digital clocks. It's a very good image, which children are familiar with, and it does speak for itself when it comes to what is turning and turning all the way around, or turning a quarter way round. And that links to teaching young children to tell the time, and quarter hours and half hours, and you're introducing fractions. So it's bringing the mathematics that they need to learn and the vocabulary bringing it to the fore. Now, remember, what we're talking about at the moment is the sort of mathematics that you are teaching with very young children. Okay. Elizabeth.
Okay, so the first one we can see there is reflection. Oh, and that's a picture of me there. That's a younger version of me there, Tony.
No.
No, it is. It definitely is. Anyway, we're talking about reflection in this picture, and we can see the mirror line. And the picture of the teacher I'm working with and myself is reflected directly across the mirror line. So I'm, instead of being my head at the top, my head's at the bottom, and the teacher the same. Instead of her head being at the top, the teacher's at the bottom, and everything else is reflected straight across the mirror line. So that's that type of reflection. Right, this one here is rotation, and there's a center of rotation. And you can, and this is quite clear that you can see that that's, well, it very much looks like a 90-degree rotation around the central point. So it's been rotated 90 degrees in a clockwise direction. And there you can see that the picture's moved 90 degrees. And if it was moved another 90 degrees, it would be round here. Anyway, moving on down to this one. This is glide reflection. What does that mean? So in glide reflection, first of all, there's a translation. So it's moved from there to there, and then it's reflected across the line. So in glide reflection, there's a translation, which moves the picture across the way, and then it's reflected across the line. And in the final one, it's a translation. So this is the original picture, and it's moved that way, or this could be the original picture, and it's moved that way. And in this picture here, we can see examples of reflection, rotation, and translation, which we would see in everyday life. So if you look at this picture up here, you can see that in this one here, there's an axis of symmetry along the middle of the pattern, and it's reflected that way. You've also got an axis of symmetry going through the center vertically, and it's reflected that way. And in this middle picture, it's rotational symmetry in this one. You can see that how many points is in this? 1, 2, 3, 4, 5, 6, 7, 8. So each time an eighth of the circle is turned, and it matches on to the little shape to the side. So it still looks like the same shape, even though it's been moved around, because it's rotational symmetry. This one here, this picture here, with this it's a little bit different because this has got a black background and this bit's got a white background. So the rotational symmetry in this one, well, what do you think it would be? Does anyone want to say what would be the rotational symmetry in this one? What would be the angle of rotation? About a fixed point.
To say that that is the black and white, you know, you've got to take the colour into account.
Yes.
It's not a quarter turn, is it?
No, I don't think so, Tony. I think a quarter turn, it wouldn't be the right background, would it?
No. So it's interesting, isn't it?
Pam, what's Pam saying?
2. She says it's rotational symmetry of order 2.
Yes, yeah.
Yes,
That's correct. In the bottom picture here, we can see the patterns here. And what kind of method are we talking about for this one? Is it reflection? Is it rotation? Or is it translation? Can you see, is there any way it can be a reflection?
This one with a red and then a gold pattern.
That could be
they've got reflections. Whereas
I was looking to see if there's a reflection in this one.
Yes.
Yeah, I think there is.
And
We've
the
got
blue patterns there, I'm showing the line there. It's a wavy line, actually.
if that were held straight, but there's also reflection, vertical reflection, but only partial, so it repeats.
Yes.
One. But Pamela says, for the 2 was given, we assume that the shapes are exactly the same. That was
Yes.
and she says that there is some enlargement, so that was for the one that you did earlier, I think.
Yeah. And this one here, as well as having reflection, you can also have a shifting, a translation. So if you look at this pattern here.
This one, you can see this sort of V shape is translated,
yes,
and enlarged, as Pamela has said. Yes, and I think the whole, everything you see here, this whole collection of pictures, show us some wonderful artwork. I mean, it isn't just everyday stuff, it's brilliant artwork, and it is traditional South African artwork. And I think when I imagine these artists creating these baskets or this murals or this beadwork, I think, do they think they're doing mathematics? Do you think they were doing math, or do you think was mathematics involved in what they were doing? And we don't often appreciate how much mathematical ideas, geometrical ideas now we're talking about, are applied in not just ordinary everyday life and business, but in art as well. So here you see it. Yes. So we're not going to analyze this one just now. We're just going to look at it. So again, there's the same question. What do you notice? And I think that's a great question to ask your learners, because you're going to build on their ideas and maybe tell them things which will expand their vision, what they see. But first of all, what do they see? And this, we want them to help them to develop their communication skills and their vocabulary.
So Ronaldo has noticed that there is more mathematics in artwork. He says this is beautiful.
Yes, and I did say it was South African art, but actually across Africa, in fact, worldwide, that's African art, but worldwide, there's a lot of mathematics in even knitting patterns and in crochet and lace work, and they weren't shown there, but that's more artwork as well that involves mathematics. And
Pamela says, yeah, it's like looking in a kaleidoscope where there are mirrors. So she's looking at reflections. And Ronaldo says they've also got a lot of that in Uganda.
Yes, yes. Okay, so beautiful artwork. And now question is, where is the center of rotation in these pictures? And each one has its own center. And where you see this sort of type of transformation involved in nature is in flowers, of course. So many flowers have got rotational symmetry, as you see here. So now you see, you're going to see more of this keyring, Santa, and now some of the secrets we're beginning to give away. Santa is between 2 parallel mirrors there, and that was the key to how that picture of the girl in the lift was actually made. More of that coming up. And then here is a cuboid, a 2 by 2 by 2 cuboid, but actually it isn't that at all. It's what we see, of course, but what we see is 3 reflections. We see a cuboid that is 1 by 1 by 2, and that is reflected in mirrors that are at right angles to each other. Now we're going to watch a video. Here's Caroline again, 2 views of Caroline between the mirrors, and you can see multiple reflections of Caroline. So we're getting more than our money's worth. Lots and lots of Carolines. I think it's brilliant. She's going to show us some wonderful demonstrations of this. So Caroline's got a cardboard box and just some very cheap mirrors, and she's going to do some wonderful things with them.
I'm going to show you the effect, and then I'm going to show you how I did it.
Caroline, sweetie, I think it must have cost, that exhibition you were talking about in Spain, it would have cost thousands of euros to set it up.
Oh,
absolutely. How much does this cost you, Caroline?
2 plastic mirrors, a box that I didn't pay for. It wouldn't be as clear, but you could actually do this with silver foil on cardboard.
Oh, I tried it with aluminium foil, kitchen foil, and it doesn't work terribly well, but it does work. And so you can actually do it very cheaply in your school, even if you haven't got much to spend. And probably somebody in your household has got one of these vanity mirrors. That's what we call them anyway.
This is the real Father Christmas right here, and you can see he's looking at the mirror behind. But if you look behind him, you can see the back of his head, and then behind that, if you can just about see that, you can see his eyes. So he's facing himself for the first one, and then again, and then again, and then again and again. If you seeing it in person is a lot easier, and it actually goes on forever, just limited by the quality of the mirrors.
You can see lots of mirrors, Caroline, but you've only got 2 mirrors in this display, haven't you?
Now I'm going to show you the setup. So there's the setup. We've got 1 mirror here. I've got my little Santa Claus. It could be anything. I've got another mirror here, and I've just used a cardboard box. Just test with lots of different things, and all you need is a cardboard box and 2 mirrors. We've got these shapes. Now they're actually the same area and slightly different front and back, because the blue's on top left corner there and the blue's on right top corner there. But if you look at the reflection, you can look at the reflection in different, you've got these different ones. They're 2 different patterns. You can see all the different possibilities depending whether it's 180 degrees or going around that way as well. And then you've also got, of course you've got not just reflections, but you've got rotations as well. So that was
what Caroline has very cleverly done there is she has, with 1 mirror, she's able to demonstrate reflections, but she's also prepared the rectangles so that if she turns it over, you can see the reflection as well.
Yeah.
And you can see in the mirror that that's what it is. And then she can do it by actually physically rotating it as well. So you can see there's one arrangement of these squares and rectangles, but what we were looking at is reflections and rotations of that same pattern. So that's lovely, Caroline. Well, a very nice demonstration. Now we're doing this sort of on the cheap because we haven't got any money anyway, but the main thing is that you can do it at home with your children if you want to, or if you're a teacher, you can do this in school, and it costs you very little to get the mirrors, and then just some cardboard boxes help you. Well, Caroline, what about your cubes? You did your cubes.
I've got my itty little cube here. This is my trusty little cube. It's 1 centimeter cube. It's 1 centimeter on every edge. And what's going to happen if I put it here? What do you think is going to happen? Let's see. I'm going to push it closer. You can see it going in a bit closer.
The good thing about this is that she can take her hand away and we can see it.
Yes.
We've got 4 cubes now. 4 for the price of 1.
So the dimensions are 1 by 2 by 2. So I've got 1 high, and it's 2 long and 2 wide. Now, how could we make that into an actual cube that's either 1 by 1 by 1? Well, if that is 1 by 1 by 1, what's the next thing that we can make a cube? It would be a 2 by 2 by 2. Well, thought about that, and I thought, well, what happens if I make a 2 by 1 by 1? Then what would happen? What if I put it that way? Well, That's not quite
well, that's a cuboid, isn't it?
cuboid, and it's 1 by 2 by 4.
Yes.
So what if I do that?
Caroline, you've got another 1 cube now. Isn't that clever? 2 by 2 by 2.
Hooray. And then this is something we do with a different workshop. I've got my, I call it 100 cube. Every face is 100 square centimeters. Now let's see if we can see this. This is a challenge. So you're going to have to visualize it a little bit.
Well, we can see most of it, Caroline. And there are 1,000 of the little ones in the big cube. That means the volume of the bigger cube is 1,000 cubic centimeters. And in the mirrors, we can see 4 of them.
Yes, but is it a cube?
No. Is it a cube? No, it's 20 by 20 by 10, if you like.
Yeah. And so what we have to do to make it a cube? I'll leave that with you. And now we've got paper with a detailed design, and what I've got is a mirror in my hand.
Caroline, now it's looking kaleidoscopic.
Yeah, you mentioned the kaleidoscope earlier. Let's see, what have we got? We've got 1, 2, well, we've kind of got 4 squares again, haven't we? And
This is amazing.
Now,
yes, 4 squares. Now, Caroline's changing the angle between the mirrors, and look what you're seeing. You're seeing more copies of the same pattern now, and like the couple we saw in the museum, and we saw reflections of those, multiple reflections, but all around them, not just in a long line. And as Caroline now, she has got reflections of that. Is that?
There's 6 there.
6 reflections. And so she's got her angle of 60 degrees, which means she's got 6 reflections. And now, well, you could get 8 reflections, Caroline. It's 45 for 8.
That is.
Yes, that looks it. Yes. So she's got 8 reflections now, and that's with her mirror at 45 degrees. 8 times 45 is 360.
Yes. And now.
And she's getting more and more. How many have you got now, Caroline? Oh.
I should have, in theory, this is 22.5-ish.
So that should be 16.
My mirror's a little bit bent. I don't have, the join isn't exact, but you can see those straight lines. It's not perfect, but you get the idea. And a child can be looking through here and really, really see, and take pictures with a camera. And actually it looks better with the camera than it does looking at it direct. You are getting a better view with the camera than I am getting by looking directly at it.
It's beautiful. It's a great demonstration. But how exciting this would be for children at home playing around, and all you need is some simple props, a couple of mirrors, and these, you know, very, very simple ways of sort of moving them at different angles. And the children will learn so much about angles and about reflections. And in the school maths, we do learn about reflections and rotations and translations, which we'll talk about a bit more. And then this comes into real life in applications in crystallography and, well, in art too. And it's such an important topic in a lot of applications of mathematics, and it's something which makes the maths come alive for children if they do it themselves. So either at home or in groups in the classroom. It doesn't cost much to set this up. It doesn't take a lot of time either, but in groups of children could work on it.
I just wanted to say that I used the boxes because we had to have straight lines. We needed 90 degrees, and that occurred to me to use the boxes to get that, so without having to construct it. Tony, you've got more exciting things for us.
Indeed, yes. You've just done this with the demonstration with your 2 mirrors at an angle, and now you can see this demonstration in the museum with this couple here, the girl with the backpack, and reflections of them. You can see the same effects there. And we'll look at the theory of this in a minute. But what you see very clearly there is a hexagon, a six-sided shape around this couple, and there's mirrors at 60 degrees, and it's producing this effect that is really fascinating.
It was a hexagonal prism, so you were going through a tunnel that was hexagonal in shape. And let me tell you, I had quite a lot of trepidation about entering it because it felt as though you were going to step into space. You could see in every direction going off to infinity. And it was like, if I step on this floor, I'm going to fall through it. It was really quite amazing. Sense of space.
Yes, now I'm very intrigued. I'm absolutely intrigued by that, because I was thinking the angle was 60, and now I'll have to think again, because your tunnel, it seems to me, if it was a hexagon, then the angles would be 120. Interesting, that, isn't it?
It was really quite bizarre. Very
That's your
fascinating.
hexagon. Here we go, because we're going to look into the theory a little bit now. And the question that we're asking is, why do reflections in two parallel mirrors combine to give a translation? Now, Caroline showed this with Father Christmas, and here you see a girl in a similar display to the one that you saw Caroline in. The girl you see who's taking photos there seems to be in a lift, and if you look, you should be able to see that 3 walls of the lift are mirrors. And the effect you see of repeated images of the girl, that is because she's between 2 parallel mirrors, and the back of the lift gives us another image, but not including the girl. And as you see, alternate reflections, she's facing you, and not everyone, but only every other one is she facing you. And in the others, she has got her shoulder sort of half turned away from you. And when we talk about 2 reflections making a translation, what we mean is that a translation just moves something along without turning it. So if you look at the picture of that young woman facing you, and then you just imagine her being pushed back but not turning at all, the 2 reflections give you a translation. If you look at the blue flag, right, and it reflects in mirror 1 to B2, the first reflection is in mirror 1, and then if you reflect B2 in mirror 2, can you see that B2 and B3 are reflections of each other? And B1 it moves by a translation to B3, but that's 2 reflections. And so this is a little bit of an illustration. We put these up to challenge people to think. And if you go to the Aiming High website and go to Mirror, there's a lot more about these ideas. And the reason it says activity for all there is we believe that quite young children can start finding out and seeing and getting excited by mathematics without making it complicated for them. So children can describe and explain what they see in that mirror, even if they're 5 or 6 years old, or even younger. And you don't have to complicate it with the maths that's on the left. And we'll come back to the answer to that question in a few minutes. But what the challenge is there is to try it out for yourself. And that's just exactly what you were doing, wasn't it, Caroline? Trying it out for yourself.
And you can use a teddy bear or something to be the woman in the mirror. And her positioning is so perfect, though, isn't it, Tony?
Yes.
It's really so easy to see that her reflection alternates.
Yes. And
she's at an angle of 45 degrees, and then the reflection is 90 degrees to herself. you look up closely at this, you can see it goes on and on and on and on forever. So it's a lot clearer photo than the one with the hexagons, because the hexagons, there was images everywhere. Whereas here, there's just one long line of images.
Yes, and this brings to mind this this children's story, Mirror, Mirror on the Wall, who is the fairest of them all? There's a link on this resource on Aiming High to a song which is called Mirror, Mirror on the Wall. It's jazz, and I like it, actually, so I put the link on it. She's moved without turning, translated, but it's two reflections that give the translation, and that picture shows it very clearly. And the no smoking sign is reflected too, again and again. This is famous. This is hundreds of years old. Louis XIV, Hall of Mirrors, which he had built in Versailles. And you can see one picture on the left, which just shows the hall itself. And now just think about it. This picture shows a group of people in the far distance at the other end of the hall. And the person taking the photo is in the real group, taking the photo, and right at the other end, there's a reflection of the group, okay, far away along the hall. You can see it's just one hall, and look at the ceiling, you'll see there the design on the ceiling.
There's 3 lamps. So if you look on the left, you see 3 lamps, and there's only 3 lamps.
And on the right, there's reflections, as you saw Father Christmas reflected, and as you just saw the girl reflected, there's multiple reflections backwards and forwards, because now we've got 2 parallel mirrors here. And as you see from the lights, the ceilings, look at it, it's many, many, many receding into the distance. So
it's going on forever.
Yeah,
but it isn't.
That had people spellbound, because it was so mysterious and miraculous to them that you could get these wonderful reflections. They could see themselves again and again and again in all their finery at the court of King Louis. Now here we've got different patterns, and they are deceptive, because on the one on the left, it looks as if you've got a rose, and in the one in the mirror, looks as if you've got some sort of flower with 6 petals, but they're not. They're just formed with 2 mirrors, as Caroline showed you, and the difference between these 3 patterns is the angle between the mirrors. And so you've got lots of symmetry here, and it's this time it's not reflection, it's not symmetry by reflection, it's symmetry by rotation. On the one in the middle, there are 2 mirrors at 60 degrees. And because there are 60 times 6 is 360, and you've got multiple reflections, but they're not repeating themselves in parallel mirrors so that they're going and receding into the distance infinitely far away. They're repeats round and round and round. And we talked about cycles before when we were doing Pathway to the Stars, like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and we're back to Monday. And in 7 days' time, we'll be doing another of these shows. But this is a cycle of 6, is a pattern which repeats itself round and round, not every 7 days, but every 6. And here you get your sort of blue and purple flower with, oh, it's got some orange and green. It's a 6-fold symmetry, and some people say rotational symmetry. Some people say the order of rotation is 6.
And it's the 2 mirrors, and that's just make it 60-degree angle. And I secured one to a box, and then just move the other one with a had a guide on the floor, and just find some really nice cloth and have a go.
Yes, it's no end to the different designs you can get with this very simple experiment. Now on the left, the rose there has got 9-fold symmetry. So if you divide 9 into 360, you get 40 degrees. So to get that pattern, you put your 2 mirrors at 40 degrees, and there you'll see a pattern which it appears to have 9 petals and has got rotational symmetry, 9-fold rotational symmetry, or rotational symmetry of order 9. Now you have to concentrate and count all the way around the one on the right, but this isn't like 12 hours on the clock or 12 months of the year cycle like that. This is a cycle here of 16. You'll see the same pattern repeated 16 times. And I've just realized, you know, Caroline, it looks like your Father Christmas 16 times.
Oh, it does, doesn't it? Oh, yes. How lovely.
That wasn't deliberate. I just saw it this minute.
And that's about that angle between your mirrors ish. You use a protractor.
Yes.
We just moved the mirror until we saw the 16 images, didn't we? And it wasn't perfect, so we're doing it by hand.
But you can see the right angles there, can't you? And you can see the right angles, 90 degrees, divided into 4, making a 22.5 degrees. So you've got your 4 Father Christmases in each quarter, which gives you 16 Father Christmases altogether.
4 Father Christmases per quadrant.
Yes, they are. So you've got 3 good illustrations there of this kaleidoscope pattern. We should be talking about David Brewster now. He lived in the 18th century. He was born in 1781 and he lived to 1868. So he obviously did a lot of work with mirrors, just like Caroline did. And maybe he started off experimenting in a similar way with just a couple of mirrors to see what effects. But of course, there was quite a lot of research going on into making better telescopes and better microscopes. And so it was very important research. It wasn't just playing and making patterns. And David Brewster was an inventor as well as being a very serious scholar, academic. And he wrote about his experiments. He did work in optics. He studied the polarization of light, which has quite a lot of important applications. He studied crystals, and I don't know anything about these sciences, not much at all, just a little bit from school physics. But crystals are very important because this is the stuff that matter is made of, and the way crystals fit together depends on the symmetries that we've just been talking about. We've just been thinking about symmetries, haven't we, in these patterns, and we've been looking at reflection as and mirror lines as lines of symmetry, and we've been looking at rotation, where we have got rotational symmetry with the pattern repeating itself. We saw 9-fold, we saw 6-fold, we saw 16-fold symmetry there. And the way things fit together, you've only got certain angles that you can make into a packing, so you can pack these crystals or shapes together, like in tiling a wall. What shapes can you tile a wall with? So there's decorative or artistic applications, but there's also serious applications in chemistry and physics.
Did you know they use bubble foam they still don't know the optimum shape for packing in foam, the foam industry that makes foam for beds and furniture. And they're investing still, and I think there's a prize for the person that gets the ideal shape, and it's based on, at the moment, the one they found is based on pentagonal and hexagonal tunnels, much like the mesophyllorine. There's actual tunnels. You've got this tunnel of pentagonal shapes going through, and then around it you've got these hexagonal shapes and interspersed with other pentagonal shapes. But they don't think that's the best one they found so far, but they don't think it's the absolute optimum one. They're still looking.
That's really interesting, Caroline. Okay, so now if you look at this, these pictures again, and you will see, we're talking about it on the video, here it is today, and you'll see that in the one on the left there are 9 copies of the basic design, and the position of the mirrors there is given by the 2 dotted lines that I put in the picture. And because 360 divided by 9 is 40, Caroline had to set the would have had to set the 2 mirrors at 40 degrees apart to get a picture like that. Now, notice you'll get the perfect symmetry with any number that is a factor of 360. But 7, for example, is not a factor of 360. So you wouldn't get it by positioning. Well, you could get it by positioning the mirrors, but it would be much harder to adjust. No, you could get it, but it would be much harder to adjust the mirrors to exactly the right angle. Now, the one in the middle we talked about before, and you can see there that the angle between the mirrors, the 2 reflections, is 60 degrees, 6-fold symmetry, and the one on the right takes a bit more counting, but it's actually 16-fold rotational symmetry. Now, we're going to ask you if you remembered about this one. Elizabeth, over to you.
Okay. So I'm just going to move you out of the way, Tony. You're kind of on this level. Yeah. So we can see here we've got 2 mirror lines. Here they are. And we've got flags B1 and B2 as shown in the picture. So flag B2 is the reflection of flag B1 in mirror 1. We have to draw flag B3, which is the reflection of flag B2 in mirror 2. So we've got to try and work out where this flag would be reflected if we reflect it in this mirror. So have a think about that. So if it's reflected in this mirror, it should be this distance away from this mirror on the other side, the reflection. So the bottom here, this part of the flag, would be somewhere around about there. Maybe even a bit more. Yeah, about, let me see, that's about, maybe about here would be the start of the picture. And it should be going like this, up that way. And then the triangle would also be over here. So can we see that in position now, Tony?
So what single transformation would move flag B2 to where you've just drawn flag B3, which is, if you can see my, somewhere about here, if you can see my cursor, in the middle of where the writing is.
So the single transformation would be a reflection, wouldn't it, across the mirror too?
Well, from B2 to B3, it is a reflection, but from B1 to B3, it is a translation.
Yes, yeah. Because it's just been moved across to a certain distance.
That's right.
So it's a translation.
And so what you see with the girl is this is a reflection of her in the other wall, in the back wall, the wall that's sort of behind this line here, right? This is, so this is this second image is her image by reflection, and she's like B1, and then she is reflected to B2, but then that is in itself reflected again, and you give the two reflections, give a translation from, this is like this girl here, I'm indicating it with the pointer, would be like B1, and then this one would be like B3.
Yeah.
So what is the connection with the girl in the lift and the diagram above? Well, I've just told you that, actually. I've given this away. And you've seen this picture. So it says Versailles with the single reflection on the left and multiple reflections on the right of the same hall. Now we're going to think a bit more about this other sort of reflection, which is called a glide reflection. And if you look at the green footprints there, you will see that, like our two hands, which we looked at the beginning of the session, which don't have any symmetry within one hand or one foot here, but there is when you look at a pair. But then as you walk along, your footprints leave marks just like you see there in the picture, and those are what we define as a glide reflection. So whereas with the tire tracks we've got reflection, with the footprints we've got glide reflection. Now, what do you notice about this picture? Have a good look at it. Some of you will know the artist, you'll recognize this sort of work and which artist produces pictures like this. Look at the birds. Focus on the birds and ignore the fishes with their white, bright eyes. Look at the birds. What do you notice? The same reflection reflects one bird to another. Same transformation. What do you see in the picture? What do you notice? So what you've got is glide reflections here. So look at the succession of birds. You have got, just looking at the birds at the top, of course, they're translations, but the birds at the bottom are reflections, but not direct reflections, but glide reflections. And they're swimming from, or flying rather, from left to right. And you've got the fish, also images there of glide reflections, swimming from right to left. It's Escher, it's a picture by Escher, and the sort of pattern that we're looking at is called a frieze pattern, because it's a strip pattern. It's called a strip pattern or a frieze pattern, and it could go on and on and on, repeating the same continuous pattern as you see a piece of it there. We're going to look at a succession of patterns now, and Elizabeth's going to talk about this first one.
Right, what transformations can we see in this pattern, and how is the pattern repeated? Well, I can see a glide reflection. You can see that if you glide along, the patterns are repeated.
I'm not sure I agree with that, Elizabeth.
Oh, would you not?
No, because they're translated.
Oh, a translation, sorry. Yes, translation.
So it's not at all easy to see what that is. But if you look at the PPPPP, you'll see that there's no symmetry. If you take a single P, there's no symmetries in it at all. because even if you go through the middle of it, it hasn't got a stick going up to match the stick going down. And that's just a translation. And it's a simple way of just symbolizing a frieze pattern. And it doesn't matter what the actual picture is showing you, we call it a motif. In this case, it's a sort of rectangular frame with a strip posted through the middle of it, which doesn't have in itself any symmetry, that design. But then it's just repeated by translations. Now we've got some more of them, so back to you, Elizabeth.
What transformations can I see in this pattern? Well, is it in the individual patterns, like this one, for example?
Well, what it is, Elizabeth, is each one of these frieze patterns, when we break them down, what we're looking at is the smallest piece of it that is a complete design. So here,
yes,
can you see my cursor?
Yes, I can see your cursor.
Now, within that, we have got a piece of the pattern, as it were, and it hasn't got horizontal symmetry because this pointy bit down here hasn't got a matching piece at the top.
Right.
But then that is the basic design. That's the sort of smallest component, and then it's reflected in that line to the other side here.
Yep, that way.
And then that whole sort of bit of pattern there, which is sort of composite already, is translated and then translated again. The code, or if you like, or a simple representation of that design is to take the letter D, which is like this half here on the left, and then to reflect it, and then to take the two pieces together and keep translating them again,
right,
and again and again. So you get the frieze pattern.
I see.
And now the next one, whoops, I went to the next one. And that one I've already revealed what we've got there. And well, it does look like a fancy H, doesn't it?
It does.
So unlike the previous one, if we take the sort of motif, I'm now showing you with my cursor and the little arrow that the motif is that half of it, of this sort of central design here, right? And then it's reflected, it actually can be reflected horizontally. So the top of that goes reflected to the bottom, give the bottom half. And it also is reflected vertically in a vertical mirror line. And this left half is reflected to the right half. And then that whole sort of fancy bow shape thing, or if you like, very, very fancy letter H, is translated along this way. And it could be, you can imagine the strip pattern going on forever to the right, and it's translated that way. And you can imagine it going on forever to the left. So there's a reflection in horizontal and vertical mirror lines and rotations, because if you look at the mirror center there, you can imagine that piece could be rotated through 180 degrees to get the one at the bottom. Okay. And that it can't be rotated, it doesn't work to rotate it by 90, but it does work to rotate it by 180.
Yes.
And so all of the same features, as it were, are in that pattern of H repeated, H, H, H.
Yeah.
So that's the way you look at these things. And as I've just been saying, it doesn't matter what the sort of basic motif is, it's the way it's repeated that's of interest here. Now, this one is like the letter E. When you look at it, it hasn't got any vertical mirror line, because the right side is slightly different from the left side of the design, as it were. If you look at this as the design here, or this is the design. But it has got a horizontal mirror line right through the middle. And it's, again, the whole thing is, so the motif is the top half, with a reflection and then a translation to move it along the strip. There's no rotational symmetry and no vertical reflections here. And this one, like two commas, first you might think it's got a vertical line of symmetry, but when you look, one tail of the comma is on top of the other one, so it has no vertical line of symmetry. What can we see in this one, and how is the pattern repeated? All of these, this is the characteristic of frieze patterns, there's translations repeating all of them. And here, what you have got is like the footsteps. So, oh, let me go back now. It's like the footsteps. Now that this involves the whole motif now, is a double thing. It hasn't got in it within itself, this double comma hasn't got within itself any reflection symmetry because of this overlap in the front here. And it hasn't got rotational symmetry. But what you have in the whole picture is not just translations. What you've got is glide reflections like footsteps. So there is a axis of that glide reflection right through the middle. And the first motif on the left here is translated to this one, but via two glide reflections, if you like. So there's a glide reflection that takes this bit of pattern, turning it upside down and that's reflecting it and moving it along to give you the glide reflection. And that's like taking the two letters PB, where you see that P and B are reflections of each other. You see, if you reflect a P in a horizontal line, you get a B, and then if you reflect it back again, you get another P. And so the glide reflection is PB, 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 and that's the pattern you've got there. Now, we're going to ask you, so I haven't said yet, but we're going to ask you to pick these transformations out for yourself and to think about it. So I hope you're paying attention. So what transformations can you see in this pattern, and how is this pattern repeated? Now we're asking the question now, we're expecting you to answer it in a minute or two's time. So I think you can see again, there is a glide reflection involved here. Or is there a glide reflection? No, there isn't. I'm wrong. There's a rotation. And where's the center of rotation? It's somewhere around here where I'm moving my arrow here, where if we rotate by that point by 180 degrees, this piece of the motif rotates to give you that image. And that's like PD. So if you go halfway through between the P and the D and you do a half turn, you map the thing back onto itself, and then you translate it along. So that one has got rotations repeated by translations. And what about this one? Have a look at it, see what mirror lines you can see if you can see any reflections or glide reflections. Can you see any rotations? What can you see? So there's a vertical mirror line. Okay, so if you take half of these petals here, then there's a vertical mirror line that reflects that to that. And everything on this side would be reflected and go over to that side, and we can't see the rest of the strip, but we can imagine it going on and on forever. There's also an axis of reflection through the middle all the way along, and you've got like footsteps, a glide reflection in there. And if you take a point in the middle here and rotate the whole strip through 180 degrees, it will map back onto itself. And so that's like, we have to take 4 letters to do that. So if you imagine going between the Q and the B and rotating through 180 degrees, so take your center between the Q and the B and rotate through 180 degrees, you get back to, you know, it maps onto itself. Again, you've got repetitions by translations. Now there are all of them, all 7. And what I've actually shown you there is I've matched D to the E, repeated E. So number 2, which is E, is matched to pattern D. And I've also shown you that pattern E, which is the 2 comma pattern, is matched to 6, which is PB, PB, PB. And what I'd like you to do now on the worksheet, see if you could do the other, match the other 5 and draw the connecting arrows for the other 5. So you can fill them in a column like that. So D is matched to 2, E is matched to 6, and what about the others? Give you a few minutes to do that. Now this is a task you could give a group of learners to do, and there are plenty to talk about there and help them to recognize the different symmetries. You could also ask them to draw their own patterns with these symmetries, and we saw one a little while ago with the birds and the fishes, but we're not asking for anything as complicated as that, just any pattern that matches these 7 types. No, this isn't easy, but see if you can do it. There we are, and there's the solution. You can check that for yourself. Now, why is this important? Why is it important that you teach about transformations and symmetry? Why is something like this, these frieze patterns, why are they interesting and important? It's because transformations and symmetry are extremely important in mathematics, in the way we use and apply mathematics in the world. It's not just about numbers and algebra, it's about shape too. And if you look at objects and creatures around you, it isn't coincidence that we've got quite a lot of symmetry in us. We've got 2 ears, 2 hands, 2 feet. We're quite symmetrical people, not perfectly symmetrical, but there's a balance. And why is it that nature has created so much symmetry? You will see in flowers that, that there's a lot of symmetry, and that's part of their beauty. And the way things fit together, why are symmetry and transformations important? Well, mathematics is about the study of patterns, isn't it? And here, when we're applying mathematics to looking at not just nature and things like flowers, but looking at how molecules are packed together in how crystals are formed, and to understand the nature of materials, we need to understand the patterns in the way that these materials hang together. And are there repetitions in the pattern, or are there no repetitions? Are they completely random? Now, it turns out that in nature, the way material, the way molecules, the way things fit together is very often involves symmetry, and there's a whole area of mathematics, a big branch of mathematics called group theory, and that is a study of, and that analyzes, and it's applied. I mean, physicists using it every day. I mean, it actually is a way mathematically of analyzing structures and how the parts of the structure interact with each other. So what you're doing when you're teaching your learners about symmetry and about transformations is paving the way for much more advanced work on the subject that is very useful in the real world. And the fact that maybe the individuals in your class don't use it themselves when they, in their adult leave school, it's part of their education if you can help to open their eyes to how mathematics is used in the real world, with just a little bit of chat about it. And now what we've analysed here is these 7 frieze patterns. There are only 7. There's no other combination of transformations that will produce a repeating pattern, only 7. Now, if we go into a pattern that covers the whole wall, and we call, a whole flat plane, we call that wallpaper patterns, it becomes more complicated, and it is known, it has been fully analysed how many patterns you can get. Now, where it becomes really useful, I mean super useful, is when you get into 3 dimensions, because you need to be in 3 dimensions before you start talking about crystals. So all we're doing is a baby school approach here to transformations and the way things repeat themselves, which we can understand. We can understand 7. We would have a lot more difficulty in analyze. Well, it's not difficult, but it would just take time. We're not going to spend on wallpaper patterns for the plane. And I think you can begin to imagine now how that might be used when it comes to crystals and 3 dimensions. And now I'm going to hand over to Elizabeth, who's got a really very simple but very, very challenging task for us to finish with.
Okay, so this is taken from the Aiming High website, and you can see that we've got 3 by 3 squares here, making the pattern. And we've to find out how many different symmetrical patterns can be made by shading some squares in a 3 by 3 grid. Okay, so we've got a 3 by 3 grid. How many different symmetrical patterns can you make by shading some squares? And it says there's more than 60 possibilities. So I think we were going to try and go into the website, were we, Tony, to sort of...
Okay, well, we will in a minute, but we'll give people some time to think about
Have a think about that, yep.
So what you see here is the same pattern as in the bigger picture on the left, but I put a red dot in it. So it helps you to see how the 4 patterns that are shown below are actually repetition of the same pattern by rotation and reflection. So if we look at all the patterns, there are actually more than 60 different ones, but we take them, but we have to sort of cut down the work. Well, it sort of cuts down the work. We actually take all the repetitions of the same pattern as one and the same. So like we take 3/6 and 2 quarters and 50 hundredths and 7 14ths as all equaling a half in what we call an equivalence class. Here we only need the basic one, and then we don't record those. Now you might like to look at this, where this is about working systematically, and if you're going to find them all, it helps to have a plan, and to have a plan of how you're going to do it. and to do it systematically. So if first of all you look at perhaps shading all 9 squares and then shading only 1 square, how can you get different patterns from shading 1 square and then 2 and then 3 and then 4? And of course, if you shade 4, you leave 5 unshaded. And as you have here, there's 5 on this green picture on the right, there's 5 white. Now, if, as Elizabeth said, we go to the website here, you'll see Symmetry Challenge there. And I want to show you the Inclusion and Home Learning Guide. Now, the Inclusion Guide is typical of, we've got about 400 different learning packs, we call them, on Learning High. And this is the learning pack for Symmetry Challenge. So here is the basic question, simple question: how many symmetric patterns can you make by shading whole squares in a 3x3 grid? Deceptively simple. And then every learning pack has got a worksheet. This is called the worksheet, and it says there's some help here for learners who struggle. And it says you could start with a 2x2 grid to help you to feel confident that you understand what to do. So if you start with a 2x2 grid, and you can get all those fairly easily, and then you can go back to 3x3, and that's a general method for problem solving. If you can't solve the problem, you don't see how to do it, maybe you can shade some, but you don't know how to find them all, and maybe you go back and simplify the problem and then work your way back to what you were really trying to do. And then these worksheets have always got a next, and this is the extension for your bright sparks. This is your extension for people who can do it, and then you before the others have had a chance to finish, you give them something else that's a little bit different but equally challenging and in its own way, but where they can apply what they've just been doing, but apply it in a different way. So here you can do the same sort of thing with a triangle pattern there. Now here are the here are the grids to do it on. Okay, so if you've got this worksheet here and you give either one of these strips to each group or each pair of learners, or two of them. You wouldn't give this one out at the beginning, and then you can give them this so that they can shade in the patterns on this grid. And then this is the poster. I call it a poster because it's actually done the organizing. So it's a systematic, it's a system for making it sort of breaking it down into smaller steps so you can check that you've got them all. So maybe you could start your learners off doing it using just grids like this without any suggestion, and then say, well, how do we know, how do we recognize whether that one's here before, or how do we know we've got them all? If we think we've got, supposing we've got 40 patterns and we think we can't see any more, how do we begin to look for the ones we haven't found yet? And then you can talk about needing to work systematically, having a systematic plan. And then the inclusion guide starts again with advice for the teacher about what you can do with different age groups. And these are the things that we were discussing earlier. So what can you do with different age groups? I'm not going to read this to you. You can look at it for yourself. But one of the things we haven't discussed is simply tearing out of scrap paper symmetrical shapes by making a fold or 2 folds in the paper and tearing it and then opening it up and seeing your symmetric pattern. And so obviously we've looked at those, and now we come on with upper primary and lower secondary to this pattern, but to this same challenge that we're talking about. But here it's how would you present it to grade 6, say, or how would you present it to the grades 7, 8, or 9? And some of the questions you could ask. So this is advice for teachers here. And then there's the grid, which does the organizing. So you could, and there are enough grids in this poster that you can get them all as long as you don't use up them by repetitions. Here are the key questions for the teacher, some of the key questions that the teachers can ask to guide learning. And then what would you do with years 9 to 12? Well, you discuss the reason why it's important, and it's an important skill to take away from school, to be able to use in life, to be able to make a plan for working systematically and make sure that you take into account all possible cases. And maybe you can get the learners to suggest some tasks which have to be done in a certain order. For example, the simple one of, if I'm going to make a cake, it really matters the order in which I do it. And so I have to have a plan in advance for how much of the ingredients, have I got them in my kitchen or have I got to go out and buy them? So in everyday life, we do plan systematically, and in business applications, it's crucially important that we do that. And then so what you would do would be years 9 to 12. You must here stress, which you might not do with the younger learners, this idea of working systematically. And here you've got the solutions. So all the solutions are given here, okay? Where you shade 1 square, where you shade 2 squares, where you shade 3 squares, where you shade 4, and you don't need to go any further. This makes a total of 64 patterns, and you've got all the lines of reflection shown in those patterns, and if you examine them, you'll see they are all different. And why do this activity? This is typical of all the learning packs and the learning objectives. There's a diagnostic assessment which you can use at the end to see what the learners have actually learnt from the experience, and then there's some more follow-up exercises there. So let's go back to our original slide here, and I think we can give you a minute or two to look at that before we actually go on. You might want to see how you could use that in your class. Maybe you get the whole class to work on in groups, perhaps, to work in a much freer style, just with the grids, and then shade in the ones that you can on a poster that you can put on the classroom wall. And if you haven't got them all, then leave it for tomorrow or next week and ask the learners to think about it and see if they can find any more that aren't on the poster. And then after a few days, see if you've got 64, and but if you've only got 60 and there are 4 more, then that's a big challenge for everybody to look at them carefully and to think about the symmetries. And so in order to do that, they've really got to exercise what do they know about symmetries. And it's a really good exercise, and you can be, really congratulate anybody who finds number 61 or 62 or 63 and then 64. Celebrate when we've got more. So here we've come to the point of the workshop where we look back on what we've been doing. And what would be really good is if some of you would like to comment, if you've got anything to say about what you've seen or what you might use. Pick out one of the activities that you might use. Tell us if you think you'd get hold of a mirror or 2 mirrors, and you do, you get in your classroom, you get set up one of these demonstrations like Caroline showed us. And here in the picture,
put pictures. If you do it, when you do it, put pictures on the group. That'd be amazing, on the WhatsApp group.
That would be really good if we could share some ideas on the GTEN group, or it doesn't matter which WhatsApp group you're in. Just share the ideas, and that would be really nice. Let us know if you've done this with any of these activities with your learners. If you look at this picture on the right, which you saw in the video, and then we get this one of the double reflection giving you a translation from B1 to B3, you'll see that we didn't give you the answer at that point. You'd already seen it in the video, and we hoped you'd then remember what to do, or you'd be able to think quickly and you'd know what to do. And there it is. And I've organized these pictures so you see that next to the girl in the lift, where indeed there are 3 mirrors involved there. And then again, the pattern at Versailles and Caroline's little key ring and the many reflections of the little Santa Claus, the ones we saw at the beginning. If any of you are primary teachers, it'd be really interesting to know which of these activities you might do with your learners in primary, and that would be interesting.
I would like to say that I find the 9 square symmetry challenge, let's say, I find it deceptive, because I am forever spotting the same one twice that's the same symmetry, just looks different. So it's a really nice challenge where you have to really understand the symmetry and make sure you're not actually saying you've got 2 when you've only got 1. It's simple, it's achievable by low attainers or young children, but it's also a challenge it's a lovely low entry, high ceiling activity. I really like that one.
I agree with Caroline there. I think the point is it is so simple. Anybody pretty much, from about the age of 8 or 9 can do that. But they won't get very far necessarily, but they can, make symmetric patterns. In fact, children do this naturally when they draw things. Sometimes they they can see, everybody's surrounded by things that are symmetrical, and I think it's so simple that young learners in primary school can begin to find some symmetric ways of making the pattern symmetric, and seeing the difference between patterns where they do some shading that doesn't make it symmetric, and patterns where you do some shading that do make a symmetric pattern. But then it's, as Caroline so rightly says, it's very much a low entry point, high ceiling. So it's very good for differentiation. Everybody can have some success, and the way in which you ask questions as a teacher is different. So you might ask the learners who struggle a bit, see how many can you find, is the same question. And you congratulate them on if they find 10. Well, that's really good. Perhaps you can find another one. And the learners who are really the bright sparks, you can say, ask them, can you find them all? Can you be sure you found them all? And that's a different question, but it doesn't appear to the children to be that different. And therefore, you're discriminating in a very discreet way by congratulating the learners who, are a bit slower, and challenging the learners who are, as I say, your bright sparks. And you should be doing that. You should be helping everybody to succeed and making them feel good about what they can do. Now, as you see, I've organized on the bottom left here the 4 pictures of Elizabeth working with a teacher there. And she talked about the 4 of them, and I've put the footsteps into the glide reflection picture, so into that part of the set of pictures, and I put the translation of this into a pattern which has just got translations like this, wherever it is, this PPPPP pattern, this one here, which has just got translations in it. There is a strip pattern of the this design that we've been looking at.
It is what Caroline said. It seems to be so easy to do these transformations, and very quickly it can get very complicated and mind-boggling, especially if we're not used to seeing reflections and translations so easy. Well, translations are quite easy, but reflection, it's the easy shapes are easy, and then it can get very complicated very quickly, right? I keep looking at the hexagonal tunnel. I don't know if you paid attention to it. I don't know if you can put that one a bit bigger, Tony. It really struck me that actually not all the images, shall we say, were exact copies of the actual one, and it's probably because of the angle it's being looked at. Bottom left is you can only see the girl, you don't see the guy, because he's hidden at that angle, isn't it?
Yeah, that's a really good observation there, Pam. I think if I had been standing lower down or taken the picture from the floor, which looks like not the floor, and looked up, you would have had something totally different. I think the angle from which that photo was taken, or from which you are looking at it is absolutely critical. Not so much when you've got 2 mirrors, but it still matters for 2 mirrors, because if you're not at the right angle for 2 mirrors, you can't see it all. So the angle from which you are looking absolutely matters, I think, for all of these.
So on the right, you see more the guy than the girl, because the mirror that will be reflecting those images will be closer to the guy than the girl, right?
Pamela, that's really, really interesting comment on your part, and I'm glad you brought it up. You see, I think that what Caroline has got there is looking through the tunnel. And what would have given you what you were sort of expecting to see would have I think the museum exhibit is designed so that when you're in the tunnel, you don't look towards the ends of well, you might look towards the end of the tunnel, but if you look in your reflection in the mirror, right, in one of those mirrors, on one of the walls of the or even the one below your feet, you would see the multiple repeating pattern, like the Santa keyring pattern was repeated, or in the Hall of Versailles. But because we're looking through the tunnel, we're getting a different view of the different mirrors. So what I think is, if you look towards one mirror, you'll get an image not just of that set of the 2 parallel mirrors and all the parallel images, but glancing towards the side, how what is on the other 2 on either side reflect in the one that's in front of you.
Masik Shaba said, I like the fact that there are 2 girls at the bottom, so you've got the reflection, their own reflection down, but at the same time you've got the talking about rotation, because of course you've got the rotation element because of the angle, I think. and he's speculating about the rotating with 180 degrees, which there was, because that 180 would have been above. So that would have been 180.
Floor to ceiling. Yes. Yeah. It is a lot in that. And I think we could have a much longer discussion. What you have here is the links for the various Aiming High learning packs on this topic of transformations and symmetry, and the video which we showed you that we made of the Happy Maths Hour with Caroline showing the demonstrations. And then I want to talk about let's play mathematically and learn. Because why play mathematically? Well, first of all, to develop a love of mathematics, but also to, importantly, to unlock knowledge, to help the learners to learn, to improve numeracy and visualization skills, to have drill and practice in a painless way, to practice mathematical procedures, to motivate concentration and critical thinking, because the learners will think hard about games in a way that they might not every lesson think hard about the mathematics. But if you put a game into the lesson and it's a mathematical game and it's mathematical learning, then they will not even think they're learning. They'll think they're just playing. And of course, it boosts confidence in mathematical ability if they succeed. And we're bringing out, AIMSEC's bringing out a series of books. And the first book will appear in March next year. And we've got a competition for teachers here to win their own free copy of the book and some of the packs of cards and things that go with it by engaging with some of the games which are on the currently and now already on the Aiming High website, and commenting on how their class reacted and what they thought of it. So if you engage in this sharing of ideas, then you may make yourself eligible for one of these prizes. So each of these games is 36, not just 36 games, but 36 sets of games. So we've got, of each game, there's a version suitable for primary, there's a version suitable for secondary or adults, and different versions for different age groups. And each comes with reflective questions and materials designed to bring out mathematical thinking and to provide a deeper understanding of the topic that underlies the game. So it's not just playing games for fun, it's playing games in order to learn. And even for the youngest learners, this can be transformational. So that's just announcing our book that's coming out, and you can have a look find out a bit more about it if you go to that link. And then how are you going to see this video when it's ready, when we've edited it, or today? And the other GTEN workshops, they're all on our AIMSEC YouTube channel. Every day we introduce a different AIMSEC learning pack by a daily starter, which you could do in a few minutes, and then you could pursue a bit longer if you were doing that topic in your lesson. And if you have friends who want to join the GTEN, then they should just ask by sending an email, and they'll get put on GTEN, or they can put it on, you can put a request to include one of your friends on WhatsApp itself. The time's come to say goodbye. Here are some links. Goodbye from me and all of us. Do you want to say goodbye, Caroline, Elizabeth?
Elizabeth
Yes,
first.
Yep, thank you for the teachers that are still on, for coming on in the Saturday afternoon late into moving on into the evening and participating in this workshop. And I'm sure, as Tony said, there's been a lot of material that you can use in your own classrooms.